almost have. Okay, yeah. Anyways, like I was saying, these numbers are very important because they will always ask you this. It's like a prerequisite to answer the question. And of course, if you know the final answer already, it's always easier to work backwards. So you can reverse engineer and roughly, you know, solve the question yourself. These numbers are very important. Please make sure you guys actually take the time to remember it. I'll put this in the group chat. Okay, yeah. Then after that, moving on to this next part here, which is the first question of the exercise. A device at the bottom of the sea emits a sound wave of frequency 200 Hz. It's always good to identify your information first. Then after it says that the speed of sound in sea is roughly this amount. This is the amount, and they want you to calculate the wavelength. Of course, if we see this kind of information, what's the formula again? All right. Okay, good. V equals to F lambda. If it's lambda, then it's V over F lah. Right, the basic formula is this one. So from here, it's just a matter of substituting the numbers in 1500. Divide by 200, which is definitely going to give you 7.5. What's the units, Rachel? Meters. Very good. Guys, you must always write your units in your exam. Okay, help me open the door, Rachel. It's always important to write down the units in the exam, guys. If you do not write your units, you definitely will lose your marks. Super important. Okay. Then after that, it says that the sound wave passes from the seawater into air. State what happens, if anything, to the frequency of the sound. Will the frequency ever change? No. Frequency in your exam is a for sure 3 marks, guys. You have to mention that the frequency will stay the same, right? Regardless of all phenomena, doesn't matter if it's reflection, refraction, or diffraction, frequency will never ever change. But when the speed of sound travels from water into air, will it be faster or slower, guys? Why? So the speed increases? No, who told you that? Oh, you know how sound travels, right? In air and solid and liquid. In air, it's vibrating the air particles, right? In liquid, particles are closer together, right? Then finally, in solid, the particles are touching each other, right? Which one travels the fastest? Solid, right? Whereas air is the slowest. So if it's from seawater into the air, and obviously what's going to happen is the speed of sound is clearly going to decrease. Excellent. It's supposed to mention that the sound speed decreases. Okay, very, very important. Make sure you understand the concept, then you know how to answer the question. Okay, then moving on to the next part. Figure 6.2 shows a water wave crossing a boundary. Mine is like this. Is yours printed like that also? What's it? Oh, wait. Okay, figure 6.2 shows water crossing through a boundary from shallow to deep waters. I think, yeah, it's from shallow to deep waters. And if it's shallow to deep water, first things first is we identify that the shallow water is faster or slower, Rachel? Is the shallow water faster or the deep water faster? No. Oh, what did I say? Forgot my story already, man. What's the story with remembering shallow and deep water? Where are you again? You're on you're on a beach, and then you imagine the water where it's super far away. Will it look like this? Or will it look like this instead? Obviously, it's this one, right? And if it's obviously this one, why is this one so damn high? Because the speed is, yeah, the deep region, the speed is faster. The shallow region, the speeds are slower. Remember this picture, guys. From here, I know that from the shallow region, the velocity is slower. In the deep region, the velocity is definitely higher. Then obviously this process that is taking place from shallow to deep region is known as refraction. So it's refraction, right? Because there is a change in speed of the wave. It's the same thing like how you see the straw bends in the water because there is a change in speed of the wave. Okay, very important. Refraction is because there is a change in speed of the wave, but you don't have to write this down. It's just for understanding sake. You just write refraction, it will have been good enough already. Okay. And finally, one box corresponding to the property of the wave is the same in the shallow and deep region. Which one is it? Frequency will never ever change. Very important, yeah? Then moving on to this next part here. If you see the gap in between these two things, this phenomena is known as what? What is this known as? If there's a gap here. Oh, why are you late again? Rockwell, what is this phenomena known as? Shen, what is this phenomena known as? If there's a gap in the barrier in the waves, what will happen? What is this thing called? When it starts to become like Wi-Fi shape already, what's it called? What's his name called? Saya? Anyone online can tell me what's this phenomena called? This is something we learned last week, right? It's known as diffraction. Excellent job, Raj. Right, it's called diffraction, and diffraction. Hey guys, I want to highlight this again. It's probably somewhere in the drawings later on. As soon as I see this, right, I see that this is compression, this is refraction, and then this is compression. Right? It means to say here to here is considered one wavelength, yeah, right? And if here to here is considered one wavelength, when I'm expected to draw the diffraction, first things first is, like I mentioned last week. Hey, you were here, right? Last week, the week before you weren't, right? Is it supposed to start here or is it supposed to start at the opening? Shen, which one? Do I start here or do I start here? One or two? Two near Number one. It should be the opening of the gap, guys. When you draw, you cannot start off with drawing like this. You will lose your mark straight away, guys. And when you draw it, the wavelength must be the same before and after diffraction also, meaning to say, like from the eye level, if this is 5 cm, this better be 5 cm and this better be 5 cm. Of course, you're expected to draw better with a pencil. I'm just drawing with a mouse. That's why there's clearly some difference in the wavelength. But when you draw it, you're expected to draw the same wavelength, guys. Diffraction does not affect the wavelength. Very important. Diffraction does not affect the wavelength. Super duper important. Always asked to be drawn. Okay. Then from here, they ask you state how a compression differs from a refraction. Guys, what's the definition of a compression and what's the definition of a refraction again? In terms of the pressure. Oh shit. Anyone online? Maybe let's see who is here. Jihin, in terms of pressure, what's the difference between compression and refraction again? Nope. Who else is here? Jaden, in terms of pressure, what's the difference between compression and refraction again? It's refraction, sorry. In terms of pressure, can anyone tell me or not? Good. One has higher pressure and one has lower pressure. So which one is the one with higher pressure? Compression, it has higher pressure and refraction has lower pressure. Guys, this is also a very important question. Compression is a region of high pressure and thus molecules are closer together. Right. Then rarefaction. And rarefaction is a region of low pressure, and thus molecules are far apart. Well, this is a very common question with a very common answer, guys. In fact, I think I made you guys write down in the notes, right? Okay. Done, everyone? Yeah, moving on. So from here, they ask you the speed of sound is somewhere around 340 meters per second. The frequency is this amount. And most likely they're going to ask you to find the wavelength, right? Because there's only one formula that relates these two things together. So if V is equals to F lambda, then lambda would have been V over F lah. In this case here, it will be 340 divided by 850. And press it in the calculator, you'll get 0.4 meters. 所以你有做好功课吗？为什么不做我功课？你去了1个礼拜，懂了，真是。会做我功课哎，数学包。下一个你一定要做啊！我跟你讲啊。Okay, then after that, from here, the next part, the time that elapsed before the compression A reaches the barrier here. So compression A is this, right? We found out that each wavelength is 0.4 meters, right? So if 0.4 here, then there's another 0.4 here, then there's obviously a 0.2 here, right? Meaning to say the total distance here is how much? 0.4 plus 0.4 plus 0.2, 1 meter apart. If it's 1 meter apart and we identify that the speed is 340 meters per second, how do we find how long it takes before it reaches here? What's the formula that we use? Good, excellent. You're supposed to use the speed equals to distance over time formula. From here, time is equals to distance over speed, which is going to be 1 meter divided by 340 meters per second, and you will eventually find a very small number. What's that very small number? Why do you use the calculator? 0.00294. And what's the units for this? What's the units for time? Oh, yeah. 0.00294 seconds, guys. Very, very important. Very, very important. Okay. And then finally, on figure 6.1, draw the shape and position of compression B and C as compression A reaches the barrier. Oh, sorry, you're not supposed to draw 3. You can only draw 2 here. Guys, why? Because they only want the compression B and C as it reaches the barrier, as A reaches the barrier. Means to say, right now A is this position, right? As A reaches the barrier, is going to be in this position, right? It means to say only B and C would have diffracted towards the right. You guys know what I'm talking about, right? So from here, in a normal scenario, you're actually supposed to draw 3. But in this specific question, obviously the parameters are a bit different, right? That's why you can only draw 2. Guys, I repeat this again. The reason why we're only drawing 2 here is because A is reaching the barrier, means to say only B and C pass through the barrier, which went through diffraction. In a normal scenario, when they ask you to draw diffraction, right, you're expected to at least draw 3 diffracted waves. But in this question, it's a bit different only. Okay? Very important. And make sure your wavelength is the same before and after. It looks a bit small, doesn't it? 这个才是你的 wavelength. A 到 B 才是你的 wavelength. Yeah. Okay. Yeah. All right. Then after that, blah, blah, state how the speed of sound in water compares to that of air. Obviously, the speed of sound is in water is much faster than air. And this is how you're going to get your free one. Easy. Oops. Okay. Okay, then the final question here before we move on to the next chapter today. It says that a dolphin produces a sound wave of frequency 7,000 over. This is obviously the F, right? Then after that, figure 6.1 represents refractions of sound wave traveling in a water. Blah, blah, blah. Hey, guys, pay attention to this. This is also a concept question, guys. They say that each and every one of these are rarefactions, right? When do you think the compression is? If this and this is a rarefaction, where is the compression? What do you say? Good, excellent. The compressions will definitely be in between the rarefactions. It also means to say if this is from rarefaction to rarefaction, right? It means to say here to here is considered one wavelength, because wavelength is as soon as it repeats itself, right? So compression, then rarefaction will be in between the rarefactions here. Okay. Then yet again in the question they ask you state what is meant by a rarefaction. How do we define this again? It is a region of we just wrote it down just now without referring. Rachel, what's the answer of a rarefaction again? Sorry? No, that's refraction. Rarefaction is the other thing, the compression and rarefaction one. In terms of pressure, how do we define a rarefaction again? Low pressure region. Understand? Hey, okay, I want to highlight this since one of you guys got it wrong already. A lot of students, they always don't read the question properly, right? They think that this is refraction. I've seen it happen for many years already, guys. There is a difference between rarefaction and refraction, guys. Refraction is this one here. Refraction is this one here, right? Obviously, this is refraction, right? The other one is the one in the sound wave that is either compression or rarefaction. They sound similar, but they are definitely different things, guys. Be very careful when you're doing your questions. A lot of students always get it wrong for me. It's not just limited to you. Okay, so from here, you're supposed to state what is a rarefaction. Rarefaction is a region of low pressure and thus molecules are further away. Simple, straightforward answer, guys. Okay, then moving on. On figure 6.1, two rarefactions A and B are labeled. The distance between A and B is 0.76 meters. Where is A and B? This is A and this is B. They say that here to here is a total of 0.76 meters here. If it's a total of 0.76 meters, how many wavelengths are there? 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength. From here, I know for a fact that the wavelength is equal to 0.76 divided by 4, right? Which is essentially going to be 0.19 meters. Right, it's going to be 0.19 meters lah. This is what I know first. Okay. Oh, then this is the question already. They ask you what's the wavelength. Right, what's the wavelength? There's 4 wavelengths here. 1, 2, 3, 4. In 0.7, then obviously you just take the 0.76 divided by 4 lah, which is going to give you 0.19 meters here. Right. Then after that, they ask you the time taken for the refraction A to reach the point of refraction B in this position here. So how long will it take for A, here, to move to B? Yet again, it's going to be the speed equals to distance over time formula, right? Because I think we're given the speed, right? Are we given the speed? Oh no, we're not giving the speed, but we're given the frequency. From the frequency and the wavelength, we can find the speed using the V equals to F lambda formula, which is 7,800 multiplied by 0.19. Press that in the calculator and you will get probably 1,000 something, I think. How much will you get? 1,482 meters per second. If it is 1,482 meters per second, the time taken for A to reach B will be, yet again, using the speed equals to distance over time formula, right? So speed would have been equals to distance over time. Time would have yet again be distance over speed, which is essentially 0.76 divided by 1,482, right? Then you press that in the calculator and you would have the answer for this time here already. Okay, you're supposed to find the wavelength, find the speed, then after that, find the time taken. Okay. Anyone confused with this part here? 你明白吗? You understand? Which part did I lose you? 7,800. And the wavelength now, which is this one now. Do you talk to Abigail, Rachel? She's feeling unwell today. I thought you guys talked about it or something. You're from the same class, right, with her? Oh no. But you know her lah. Okay. Yeah, if you press this in the calculator, how much do you get? 5.13. 5.13 times 10 to the power of negative. How much? 4. 4. 对吧？这个 let me check the answer. I don't remember it being this answer though. Wait, is this that question? No. Oh, it is. You were right. And I was left. 5.1213 lah, right? Because it's 3 significant figures only. Guys, I want to highlight this. You see the mark scheme here? They see 5.1282, blah, 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 all this nonsense, right? Don't ever write this in the answer, guys. Your mark scheme will not accept anything more than 3 significant figures. Means say 1, 2, 3, maximum already. Alternatively, if you wrote 5.1 times 10 to the power of negative 4 is acceptable as well, because the minimum amount of significant figures is 2 in your answers, guys. It cannot be smaller than that, right? So 2 or 3 significant figures. If you want it to be easy, then just go for 3. Okay. Right, then the final part. The sound wave passes from water into wood where the speed of sound is greater. State what happens to the frequency. Obviously, no change. Good. Then after that, the wavelength when the speed is greater is going to be increased as well, right? And then from figure 6.1, sketch the position in the wood of the three incomplete rarefactions, right? It says that the sound wave is greater speed right now. If it is greater speed, initially it's supposed to be straight line like this, right? Rachel, will it lead forward or will it lag behind? Will it bend towards the right or will it bend towards the left when the speed is greater? It will bend towards the right. Excellent. And when you bend towards the right, make sure that the first two lines are parallel. Then after that, the rest of it just follow. Make sure that all of them are parallel to each other. Obviously, you're going to use a ruler to draw this. I don't have a ruler, so it looks a bit crooked, guys. Yeah. Make sure it's a straight line with your ruler. Sure, why bend to the right when the speed is faster? Of course, it's going to bend to the right line. If not, it's going to bend to the left, man. This one here, the speed is faster. Speed is faster means to say the wavelength is going to be greater also. If I were to bend towards the left, which is something like this, yeah, something like this, can you see that the wavelength actually decreased or not? That's not going to make sense, right? It must bend towards the right because the speed is faster. This is a scenario I call leading forward. Only when the speed decreases, it lags behind and bends towards the right. But if not, speed faster, for sure it bends towards the right. Okay, everyone, you are done. Okay, let's move on to the next chapter. Anyone got any questions for this part here? Anyone? Like anyone at all don't understand anything I've been talking about so far? If not, then let's move on to the next chapter.
Why the wavelength increase?
Because according to the formula, V equals to F lambda. You see here, if we follow the V equals to F lambda formula, right? If the frequency remains the same and the wavelength, the speed increases, for sure the wavelength is going to increase. If I want to put numerical numbers, let's say frequency was 5. When the speed from 5 increases to 10, you can see that the wavelength increased from 1 to 2. Right. So this is just a mathematically proven way to say that when the speed increases, the wavelength for sure increases. Okay. Okay, excellent. Let's move on to the next chapter here. Okay, next chapter. This is basically going to be the wave chapter, guys. There's going to be a lot of things that you're going to learn about, but let's go through it one by one. Now, first and foremost, for the light wave chapter, the first thing that you're going to be introduced yet again is going to be the reflection of light. Last week or the week before, we were talking about the reflection of water wave, right? This one is the reflection of light waves. And this one is the refraction of light waves here, okay? For light waves, it is very, very straightforward. I'm pretty sure everyone here has experienced this. If you ever stood in front of the mirror of vanity, right, you'll notice that as soon as you stand here and you lift your right hand, inside the mirror, there will be the exact same guy doing the exact same thing, but is laterally inverted. Laterally inverted means to say if you're raising your right, this guy will be raising its left. Right? This is what we call the phenomena of laterally inverted. Okay. Now, of course, in your IGCSEs, they won't only ask you about the understanding of laterally inversion. They'll usually ask you to draw the light ray diagrams to locate your image. So if, let's say, I say that this thing is the object, and this is the image, they'll ask you to draw light rays to indicate how they form the image. And if they ask you to draw light rays, you're supposed to find a point of interest. For me, let's say the point of interest is here. I want to find out how this hand is going to be constructed in the mirror. when you draw the light rays, you need to draw at least two, yeah. So if you're drawing two, you know, like how normal light ray is going to work, right? If let's say they ask you to draw only one light ray, you just draw like this, right? It's like how light works in the mirror, lah. Right, it's supposed to just go straight and find it there, ma. If you ever shine a torchlight into a mirror before, you'll see that the light goes straight, ma, if you're hitting it perpendicularly. But of course, in your exam, they will never ask you to just draw one light ray. They'll ask you to draw two light rays instead. And if they ask you to draw two light rays, you're supposed to draw a V shape. You're supposed to draw a V shape that hits the mirror. Obviously, this light ray that hits this side of the mirror will be reflected this way, right? And obviously, this light ray that hits this side of the mirror will be reflected this way here. Normal scenario. So how will the image be formed here? You're actually supposed to draw some virtual light ray, guys. You're supposed to draw a virtual light ray that is represented in a dotted manner. You're supposed to dot it here. Oh, bear in mind that this and this is one straight line. It's just that I'm drawing with, yet again, the mouse. So it looks kind of not straight, but in reality, these are straight lines. You're supposed to find it from the ruler. And wherever these two lines intersect, that is where your image is going to be formed. Super important, guys. They will always ask this in your exam. Anyone don't understand what I'm talking about or not for this light ray here? Very, very important. You need to draw two of it, and you need to know how to draw the virtual light here, guys. These are considered to be virtual light. That's why it's represented in dotted manner. This is considered to be real light, which is essentially how the light is going to behave. You know, like the light doesn't go into the mirror, right? It's just going to be reflected away from the mirror. But how will we know that the images are formed? Is because there's a virtual light going into the mirror, guys. Very important, this part here. Anyone don't know what I'm talking about? Good. I'm going to ask you guys to draw this later on, by the way. So if you look here, you know, basically this is just a more complex diagram of what I've drawn. From the start, if this is the object, right? If this is the object here, you could draw just two light rays, but in this example, they gave you 6 light rays. All these 6 light rays will all be reflected from the mirror, right? All of them will be reflected from the mirror. So how will the light rays go? How will the image be formed when the virtual light goes into the mirror? Okay, it's not real light. The real light reflects away from the mirror. The virtual light is the one that goes into the mirror and let us see that it is inside there. Okay, very, very important. Okay, so of course from here, the image formed from the mirror is definitely going to be virtual and laterally inverted. Laterally inverted means left side, right? Can send a soft copy of these files. Oh my god, right? Let me send it to you right now. Wait up. God. Okay. God, it's not here. Wait a minute. You are in this group. Jesus. Oh God. SM2 now. Stupid WhatsApp. Okay. Yeah. Okay. So then after that, an image is said to be virtual when the light does not actually pass through the location on the other side of the mirror. Like I keep saying, the real light is actually going to be reflected away from the mirror. It only appears to the observer as though the light is coming from the location. If you are uncertain of this phenomena, please, I highly recommend all of you guys go back home and play with your mirror, shine a torchlight in, shine a laser in or whatever. You'll notice that the real light actually bends away. That's why if you have a wall here, you'll see that the light kind of shines onto here. But if you look into the mirror, it seems like the light is going in like this, guys, right? Because it's just a reflection of this. Okay? Yeah, I will play with it for those who are unsure. I never had a childhood. Right. So from here, law of reflection states that same thing lah. Angle of incidence must be equal to angle of reflection. Like I mentioned in the previous chapter, guys, the angles here are always with reference to the normal. So how is this normal coming to be? Let's imagine today, you know, like the light ray hits this mirror here, right? The normal, guys, the normal will be constructed perpendicularly on the surface where the light rays hit. And from here, this is the incident angle, this is the reflected angle, this is the incident ray, sorry, this is the incident ray, reflected ray, incident ray, reflected ray. This will be the incident angle. This is obviously the reflected angle. Same thing, incident angle here, reflected angle here, okay? Incident angle and reflected angle must be the same. This is the law of reflection, which is obviously common sense at this point, right? The incident ray, the reflected ray, and the normal all lie on the same plane. They all are on the top of the mirror, guys. It's from the same plane. Your incident ray will not be here. Your reflected ray will not be here. Your angles, everything won't be from here, guys. It's all from the same plane here. Okay. Anyone's got any questions from this? Oh, I didn't give you the notes yet. Everyone's been staring at this. Hey, what's the stapler? Something. Hey, pass you home. Here. Okay, guys. Can you copy this down real quick? You just need to write the virtual and laterally inverted statement. Okay, then moving on to the next part here. This is a more fun phenomena, which I personally like. It's basically the refraction of light waves here. Now, if you talk about refraction, yet again, it is the same old boring example. You have a cup, right? You have water inside. You have a straw that looks normal on top. Then your straw is like bended and crooked at the bottom of the water already. Why does this happen again? Because there is what? Change in what? Good. There is a change in speed of the light. If I look from here, the speed of light is going to be somewhere around 3 × 10⁸ meters per second, right? This is the speed of light. And if I look here, right, the speed is slower because it's in water, right? There's a medium. Maybe it's 2 × 10⁸ meters per second. And because of the difference in the speed of light, we will definitely see different scenarios here, okay? Now, in refraction of light rays, usually the most common example is when you're standing on top of a swimming pool, right? Let's imagine today you stand on top of a swimming pool here, right? And this swimming pool is actually damn deep. But every time you stand on top of a swimming pool, you look down and you kind of see like, oh, it feels like it's very shallow. Have you guys ever had that phenomenon before, right? You know why it looks shallow? It's because, right, real light, if we draw it in a single light ray, guys, which they'll never ask in an exam, it will always be 2. But for understanding's sake, this is how the light ray travels. The light ray, when it goes from an eye to the water, right, what's going to happen is because there is a change in speed of the light, this light ray is actually going to bend closer to the normal here. Okay, it will bend closer to the normal and it will hit the ground here. But our brain, guys, perceives light to travel in a straight line. And because we think that light only travels in a straight line, this is what we see, the one in red line, but this is what we think we see. Okay, we think we see this here, right? And this is how we see the shadow, the depth of the pool. We'll think that, oh, this pool looks so much more shallow because we think that light travels only in a straight line. We think, guys, we think that the light ray will be from here all the way until here. But in reality, the light ray actually bended when it went into the water, and thus it, it bends closer to the normal and it comes down here. You will see that the red line is where real light is happening. The blue line is the imaginary line that our brain has tricked us all upon. Okay, and this is the reason why whenever we stand on top of a swimming pool, it's much more shallow than others. For me personally, I've actually went to this 10-meter deep swimming pool before, and I look down. Oh, it's not that deep. Do you know how deep is 10 meters? 10 meters is 5 times my length now, by the way. I'm like almost 100 AD, right? Yeah, 你几高啊？啊？你110啊？我矮你2 cm， 我179。But anyways, that's like 5 times my length. But you always think that the pool is much more shallow because we perceive light to travel in a straight line. Okay. So how will light actually travel? Of course, in an exam, they'll never ask you to draw just one light ray, but you need to understand this. Before I proceed on, anyone unclear with what I'm talking about or not? This is where the image is, and this is where the object really is, guys. We think that the light rays are traveling in a straight line, but in reality, it's bended already. Okay, anyone uncertain with this part here? Okay, then of course in exam, how would they like you to draw? It will be the same thing now. Okay, in exam, right, they'll structure it like this. Okay, they'll say that, oh, right now there's like a cup here or water or whatever it is now, and then they'll say that your eye is here. Okay, then they'll say something like, okay, guys, draw 2 light rays to construct the image of this object here. Okay, let's say the object is somewhere here. You see that this is your object here. Draw 2 light rays to construct where the image of the object will be in the water, right? So if they ask you to draw this, first and foremost, I want you to, a lot of students they like to draw from the eye. Don't draw from the eye, draw from the object instead. The object, if you draw from the object, you should have yet again the V lines again. So you're gonna have something like this, and then you're gonna have something like this. Okay, you're gonna have a slanted V or whatever, right? Then once you have this already, right, what you're supposed to do is you're supposed to draw the normal, because that's where the light ray is, right? And then you're supposed to remember that the light bended closer to the normal, right? So, oh God, my eye level is not bright already. I'll reverse draw it. In the exam, it will be much easier because it's like following a format already. Okay, it looks something like this. Oh God. Shit, man. Drawing so shit. Yeah, something like this. Right, and this is where your eye will be. Okay. So in reality, how you're actually supposed to do it, right? You're supposed to think that this light ray is supposed to travel straight, then bend. The light ray is supposed to bend closer towards the normal. This light ray is supposed to travel straight and it's supposed to bend closer towards the normal because it goes from air into water, right? And your image, guys, your image will be by continuing this line. You're supposed to continue this straight line here in a dotted manner. Same thing for this one. So you're supposed to continue this straight line here in a dotted manner. Wherever these 2 light rays hit, right, this is where the image will be. This is the real object. This is where the image will be. The image will always be much more shallow than your object, guys. Very, very important. If you drew your image to be deeper than your object, I'm so sorry, my friends, you are wrong. Okay, very, very important. Your light rays should create an image that is more shallow than the object itself. Okay. Anyone unclear? Of course, if you want to see a nicer drawing, which is not hand drawn by me, it looks something like this lah, right? It's supposed to be a straight line. It's supposed to be a straight line here, supposed to be a straight line here. But the light ray, when it hits the water, will bend. The light ray, when it hits the water, it will bend. And this is where the real thing is. This is where the image is. The image will always be much more shallow than the real object. Okay. What do you mean by alignment? Okay, so from here, refraction occurs when light travels from one medium to another. Whenever we talk about one medium, the first medium here is going to be air, and the second medium here is going to be water, guys. Whenever you see this word, one medium to another, just think that it's going to be water, air, or glass only, guys. These are three different mediums which they could ask you from. Okay, of course. The medium could be either less dense or more dense. For example, air is definitely going to be less dense. That's why it's on top, right? The medium water is definitely going to be more dense. That's why it's at the bottom, right? So from here, I wonder why the bottom of the pool always seems more shallow than it actually is. This is because light is bending when it travels from one medium to another, which is going to be water here.
Medium is always going to be.
It could be glass also. Yeah, so it depends on what medium that light is traveling, right? For example, right now you see this is because the light is traveling from the reflection and whatnot, right? So this is the air medium. If I shine this into water, then the medium will be water. If I shine this into a glass prism here, then that medium is going to be the glass. So whenever we talk about the word medium, it's going to be either air, water, or glass, right? Okay. Okay, moving on. Oh, you're going to be expected to draw this. So anyone that's not certain, better make sure you know what's going on here. You will be asked to draw this in your exam. Very, very important. Okay. Then the final part here before we end the day is basically understanding how light will behave when it enters through different mediums. Now, if we want to go for a very simplified conclusion, if let's say this is a glass prism here, like not prism, like glass block here, right? What's going to happen is, right, when light enters from air into glass, because this one here is obviously more dense, right? It's more dense. Oh God, whatever, more dense. Because it is more dense, light is actually going to travel faster or slower, do you think, in a more dense medium? Do you think light will travel faster or slower in a more dense medium? Good, it will be slower. And because it is slower, right, what's going to happen is initially, if it is the same speed, it would have been like this, right? But because it is slower, yet again, the lagging behind scenario works here as well. It will bend closer towards the normal. This was the original path. It will bend closer towards the normal here. Okay. But when the light rays enter from a more dense to a less dense region, which is from the glass back into the air, by right, the normal path should have been like this, right? But because the speed of the wave speeds up, it's obviously going to lead forward again and thus bend away from the normal. Guys, I get it. I repeat, the light ray is supposed to come here, right? Then when it enters a medium, which is more dense, because the speed of light slows down, it will bend closer towards the normal. But when it leaves the glass block, right, what's going to happen is, because the speed of light is faster, yet again, it will bend away from the normal. Here, one thing I want to highlight is that the angle here, guys, this incident angle will be the same as this incident angle here, because these two are both the same air, right? So the angles will be the same. And because those angles are the same, it means to say this angle, which is the normal to the light ray, or the light ray to the normal, these are what we call the refracted angle. This is not the reflected, this is the refracted angle, guys. When light enters from less dense to more dense, it will bend closer. When light enters from more dense to less dense, it's going to bend away. Okay? Anyone not sure what I'm talking about for this part here? Good. So if you look at these statements here, each and every one of it makes sense. Light passing through a glass block at right angles to the surface will not be refracted. The ray will pass straight through. If today my light is entering the glass prism at a 90 degrees, it will not refract. It will just go directly straight through here. The incident ray and the ray which goes back to the air both are parallel to each other. Yes, correct, Raj. That is a very good question. Guys, since we are on this as well, guys, for this one here, this light ray and this light ray are actually parallel to each other, guys, because the angles are obviously the same here. Okay, very important. Okay, so from here, light passing through here, if it's 90 degrees, it will not go through any refraction. If it is from air to glass or water or whatever, because it's entering from less dense to more dense, the speed of which slow down and bend closer towards the normal here, right? And light travels from air, which is less dense, not less dense, is less dense to glass, which is obviously more dense, right? Light will bend towards the normal here. Okay. And finally, when light travels from more dense material to less dense material, it will yet again bend away from the normal. You can see that it bends away from the normal here. Okay. Everybody. Okay, so final stuff here before we end the day. Why does light bend away when passing through different mediums? Is simply because refraction is occurring, and refraction occurs because there is a change in speed of light. Guys, always remember this. Refraction can only occur if there is a change in speed of light. Refraction can only occur when there is a change in speed of light. Yes, frequency will stay the same regardless of whatever phenomena, unless stated otherwise. Okay. Now, after that, angle which light is being refracted can be calculated using the refractive index. We will learn how to do the calculation next week for refractive index. Refractive index is defined as the speed of light in a vacuum divided by the speed of light in the medium. Don't worry, these are all parts of the formula as well. And from here, the higher the refractive index of the material, the higher the bending of the light. For example, vacuum has 1 refractive index, air has 1.003. Water, which is more dense, obviously has more refractive index. Glass will be higher, and diamond, which is the most dense, will have the greatest refractive index here. Now, fun fact before we end the day, guys, in regards to refractive index, you know how refractive index can affect the beauty of a jewel or not, guys? If today you go to Pokong, right, and you buy a real diamond versus going to the Pasar Malam and you buy a plastic diamond, straight off the bat, you'll notice that the real diamond is more shiny and bright. Do you know why it's more shiny and bright? It's because this thing here has a huge refractive index. It has a huge refractive index, meaning to say the light that travels in here is very easily reflected and goes inside the thing before coming out again. Okay, that's why if you see the very, very expensive diamonds, right, it seems like they're glowing itself, right? It's not glowing itself. It's just that the light that enters it is actually being reflected inside before it comes back out. That's why it seems like it's a glowing effect, right? But for the shit diamonds that you buy from Pasar Malam, right, because the refractive index is obviously much lower, right? Even if it goes in, at most maybe it will reflect once, then it will come up. That's why the shit diamonds will always look more dull than the real diamonds. The real diamonds have a higher refractive index. The light can play inside a little bit more. This Pasar Malam one has a shit refractive index. That's why the light will probably not even reflect inside. Like honestly, like if I were to see it, it probably will just come out straight away like this. But for understanding's sake, you just imagine this here. Okay? That's why sometimes you see like cartoons, the stupid diamond, when they open the box, the diamond is like shining, right? It's It's not shining, guys. The diamond itself will not shine. It's just that it's reflecting the light from the environment. Okay. Everybody, yeah, we'll stop here today. Please don't lose this paper. We still have quite a fair bit to go before we're done with this chapter here. We'll continue this chapter next week, yeah, guys. If you have any questions, you're more than welcome to stay back. If not, that'll be it for today, guys. I'll see you all next week.